In the rapidly evolving world of biomedical AI, one of the most persistent challenges is how to classify complex high-dimensional data, like medical images, into meaningful clinical categories. Traditional machine learning methods, while powerful, often struggle when faced with subtle distinctions between disease subtypes, overlapping classes, or limited sample sizes. But what if we could draw inspiration not from classical computing, but from the principles of quantum theory? Today, we dive into a groundbreaking approach, a quantum-inspired multi-class classifier based on the pretty good measurement, applied to two critical real-world problems in oncology: lung cancer subtyping and prostate cancer risk stratification. This isn't about running algorithms on quantum computers. It's about borrowing the mathematical elegance of quantum state discrimination and using it to build better, more principled decision rules for machine learning, all on classical hardware. Let's unpack this step by step. At its heart, classification is about discrimination, distinguishing one class from another. In quantum mechanics, this is formalized through the problem of quantum state discrimination, how to tell apart different quantum states when they're not perfectly distinguishable. The Hellstrom measurement gives the optimal solution for two classes. But what if you have 3, 4, or more? That's where the pretty good measurement comes in. PGM is a systematic way to construct a single measurement, what we call a POVM, positive operator valued measure, that can discriminate among any number of quantum states with high success probability. Crucially, it does this without reducing the problem to multiple binary comparisons, which is how most classifiers handle multi-class tasks today. This makes PGM inherently natively multi-class, a rare and powerful trait in machine learning. Here is how we adapt this idea to real-world data. First, we take each patient's radiomic feature vector, say, hundreds of extracted features from a CT or PET-CT scan, and map it to a density operator in a Hilbert space. This is the quantum encoding step. The choice of encoding, whether amplitude-based or stereographic, can influence performance, and we'll come back to that. Next, for each class, e.g., adenocarcinoma, squamous cell carcinoma, we compute a quantum centroid, the average of all encoded training samples in that class. This centroid is typically a mixed state, even if individual inputs are pure, because the averaging process introduces entanglement-like structure in the representation space. Now comes the key. We define a class-conditional POVM using the PGM framework. We start by computing the overall mixture state, a weighted average of all class centroids, then construct measurement operators that maximize the probability of correct classification. These operators are derived from the Moore-Penrose pseudo-inverse of the mixture state, ensuring numerical stability even when the state is singular. The final measurement is completed by adding a correction term on the kernel of the mixture, making it a valid POVM. The score for each class is then simply the trace of the measurement operator with the encoded input. X equals TR, F letter 1d6 rho X. These scores are probabilistic, sum to 1, and directly reflect the likelihood of belonging to each class. And the final prediction. Just pick the class with the highest score. This entire process is fully classical, no quantum hardware required. But it inherits the geometric intuition of quantum decision-making. The better separated the class centroids in state space, the easier the discrimination. Let's ground this in reality. The first case study, non-small cell lung carcinoma, NSCLC. NSCLC accounts for 85% of all lung cancers and includes several histological subtypes: adenocarcinoma, squamous cell carcinoma, large cell carcinoma, and a not otherwise specified NOS category for ambiguous cases. The challenge: these subtypes often have overlapping radiomic signatures, and multi-center CT data introduce batch effects from different scanners, protocols, and segmentation methods. The second case, prostate cancer, PCA. Here, the goal is risk stratification, distinguishing low-risk from high-risk tumors based on PSMA, PET-CT scans. Traditionally, this relies on the Gleason score, but it's limited by biopsy sampling bias. Radiomics offers a non-invasive alternative. Both datasets are publicly available, well-documented, and have been used in prior studies with rigorous validation protocols, making them ideal benchmarks. To ensure a fair comparison, we use the exact same data splits, preprocessing steps, and feature selection pipelines as the original studies. This includes combat harmonization to correct for multi-center variability, lasso-based feature selection to reduce dimensionality and prevent overfitting, stratified 80-20 train test splits, repeated multiple times for statistical robustness, grid search with 5-fold cross-validation to optimize hyperparameters, encoding type, rescaling factor, and number of tensor copies. We tested 3 configurations for NSCLC. Binary, SCC versus ADC. 3-class, SCC, ADC, LCC. 4-class, adding the NOS group. And for PCA, multiple feature subsets including robust and fine-tuned predictors. Let's start with NSCLC. In the binary classification task, the PGM classifier outperformed all classical models: discriminant analysis, SVM, KNN, naive Bayes, decision trees, and even ensemble methods. It achieved 58.57% accuracy and an AUC of 95.7%, matching or exceeding the strongest baseline. In the 3-class case, PGM remained highly competitive, with a macro-averaged accuracy of over 53%, again beating most individual models and coming close to the ensemble. But here's where it gets interesting. In the 4-class setting, performance dipped slightly. The NOS class, being heterogeneous and radiomically similar to LCC, introduced significant class overlap. The geometry of the state space became more complex, and the PGM, while still robust, didn't dominate. This is not a failure, it's a feature. It reveals something profound. PGM performs best when class separation is geometrically favorable. When classes are well separated, PGM leverages that structure effectively. When they're not, the inherent ambiguity becomes harder to resolve, even with quantum-inspired reasoning. Now for prostate cancer. Here, the PGM classifier didn't always lead, but it was remarkably close. It achieved 79.52% accuracy and 85.75% AUC, matching the ensemble model almost exactly across multiple feature subsets. But the real insight comes from the parametric analysis. When we looked at sensitivity, specificity, precision, and F1 score across different feature sets, we saw that PGM often traded off sensitivity for specificity, and vice versa, depending on the feature subset. This is clinically meaningful. In risk stratification, false negatives, misclassifying a high-risk patient as low risk can be catastrophic. So you might want to prioritize sensitivity. Conversely, if you're trying to avoid unnecessary biopsies, specificity becomes key. PGM naturally allows for this kind of cost-sensitive calibration by adjusting class priors or decision thresholds, making it not just accurate, but clinically adaptable. So what does this mean? PGM is not a magic bullet. It doesn't universally outperform classical models. But it is a mathematically principled, inherently multi-class framework that avoids the pitfalls of 1v's rest or 1v's 1 decompositions. It introduces a geometric inductive bias, favoring problems where class centroids are well separated in the encoded space. It's stable, interpretable, and flexible, allowing for clinical calibration via priors and thresholds. And it works on classical computers, making it immediately applicable today. This isn't just theory. It's a practical tool for high-dimensional biomedical data, where noise, small samples, and subtle patterns are the norm. We're not claiming quantum advantage here. We're not using qubits or quantum circuits. But we are using the language of quantum information, states, measurements, POVMs, distinguishability, not as metaphors, but as powerful mathematical tools for building better classifiers. And the results speak for themselves. From lung cancer phenotyping to prostate cancer staging, PGM-based classification delivers competitive, often superior performance, especially in simpler, well-separated multi-class settings. It's not replacing classical models. It's expanding the toolbox. The future of AI in medicine isn't just about bigger models or faster hardware. It's about better reasoning, more principled, more interpretable, more aligned with the real-world constraints of clinical data. Quantum-inspired methods like PGM offer a path forward, not by chasing quantum supremacy, but by borrowing the deep geometric insight of quantum theory to build classifiers that are not just accurate, but meaningful. So the next time you're faced with a multi-class biomedical classification problem, whether in oncology, radiology, or genomics, consider this. Sometimes the best way to make a decision isn't just to learn from data, but to think like a quantum state. Because in the end, the most powerful AI isn't always the most complex. It's the one that understands the problem,